We are ready to go, folks. I see we've got 12 people online here so far. This is Roger Messenger. I'll be your instructor today. I'm going to first check to see whether there is any messages forthcoming from PDH. And if so, we'll see that in the chat box or perhaps in the Q&A box. All right, what I need to know is whether everybody can hear me. So I need for you to find your chat box, which should be, depending on where your toolbar is. My toolbar happens to be at the top of my screen. And on the far right-hand side, there is a More option. Clicking on that More shows where the chat box is. Okay, Eric, I see you can hear. Dan, okay, we're good. If one hears, all hears, is generally the situation. Okay, I'd like to welcome you all to our experiment in the ultimate social distancing. And have to let you know, after 35 years of teaching electrical engineering, 2 o'clock in the afternoon is the absolute worst time in the world to teach a class because I'm so used to my students falling asleep on me. And I hate to admit it, but I think some of them are used to me falling asleep on them. So we're going to try to avoid that this afternoon by making this material useful and interesting. So we're just going to do the best we can to do that. In terms of my own personal experience, this is almost my first love because way back in 2005, South Florida got hit by a nasty Hurricane Wilma. I happened to be out of the state at the time, but watched the TV set, said that 90% of my county was without electric power, which meant that I probably knew more about what was going on than anybody in the county did by watching it from someplace else. And when I got back, I had been a part of an electrical contracting company back then, and we kicked it around a little bit and decided that people are getting tired of going to the gas station for gasoline. What they need is, and what they probably want, is a reliable, quiet, pollution-free system to provide electricity for their refrigerators and certain backup loads after a hurricane. And that was when we first got started. Actually, we had done a couple of practice installations before that, but we got very serious about doing battery backup PV systems back in the 2005-2006 timeframe. What you see on this opening slide here is the today's version of a battery backup photovoltaic system using the Tesla Powerwalls. But we're going to start out with some very basic stuff here today. The whole idea being that when you leave here, you will know where to find the information necessary to do a design of a battery backup photovoltaic system. It will be in the set of slides, and it will also be on the reference book reference in the on the website. So how do you get slides of the webinar? You simply ask for them. When the webinar is over, you go to the website, you can pick up your certificate of completion, and also for free, no charge extra, you can download a set of slides for the program. And since we're getting pretty comprehensive here, I have added an additional design example that will probably go beyond the time allotted, but if you order the slides, you get an additional design example. So we've got a lot to accomplish. Let's get moving. One thing that happens, by the way, is when I advance my slide, it takes my chat box away. So if you want to communicate, I need for you to type in the question and answer box. Okay? So, all about the inverter. And Okay, I'm going to clear my screen just a little bit here. And the inverter that is used in battery backup grid-connected photovoltaic systems is called a battery backup grid-connected inverter. What a surprise. And what do they do? Well, they act as alternating current or AC current sources when they're feeding the grid. And that is very specific as a current source, not a voltage source. The grid itself is basically a voltage source that maintains pretty steady 120 volts or 240, whatever you're plugging into, or 208 or 480 or whatever. And when the photovoltaic inverter feeds the grid, they are synchronized by the grid voltage. So the current that comes out of the inverter is exactly in phase with the voltage that the inverter sees. Okay? But if the grid goes down, the inverters immediately sense that and switch over to a voltage source mode, and they disconnect from the utility and monitor the utility while simultaneously feeding AC voltage and power to selected standby loads. Okay? If the grid is up and the sun is down and the batteries need some battery charging, these inverters will charge up the batteries so they don't need additional charging unless you program them to not do that. Because maybe you want the sun to charge the batteries in the morning. On the other hand, if your batteries are charged, then any electricity that's made by the sun is either going to be used by the loads of the occupancy or it's going to be sold back to the utility, more than likely, depending on what kind of an interconnect agreement you may have with the utility. So, but they have the option of acting as battery chargers when the grid is down, or grid is up, sorry, and the sun is down. And the input of inverters is basically the battery voltage, somewhere around 48 volts. And so they don't need to do maximum power point tracking. What does that mean? Well, simply that the photovoltaic array is going to be operating at some voltage different from 48 volts. More than likely, it's going to be operating somewhere in the 80 to 90 volt range for a battery backup system, but it may be operating in the 300 to 400 volt range as well. It all depends on the system. So what has to happen is between the photovoltaic array and the inverter, something has to convert the voltage of the array to the input voltage or the battery voltage. And in order to do that, it has what's called an electronic maximum power point tracking function, where it simply causes the photovoltaic modules to operate at their maximum power point so they capture as much sunlight as possible given the particular illumination conditions. Okay, but this maximum power point tracking is found in standard straight grid connect, no battery type inverters, where they're directly connected to the grid rather than to batteries first. And but it's not found in the straight battery backup inverters, as are several other functions. They don't need to do ground fault detection and interruption or arc fault circuit interruption either, usually, because that's done by separate devices in a separate component enclosure. They do need to be a part of a rapid shutdown system. Recently, the code has decided that it's not a nice idea to have high voltages coming from the roof down to an inverter or a source circuit combiner box or something, 40 or 50 feet away from the array. If the building catches fire and the fire department is there and they cut through a 200 volt wire, that's not a happy camper if the fireman is trying to do that up on a roof. So recent code changes have now required as a functional requirement, and that the system be able to shut down so no power leaves the array itself if there's nowhere for it to go. Okay, so well, pretty obviously the inverters don't make much noise, and they certainly don't pollute very much because the sun is very non-polluting. So if the grid is down, you have a source of power that runs on batteries and does not generate any kind of noxious fumes or noise that keeps your neighbors awake at night. They save on trips to the gas station when the grid is down, and that's a gas station is the last place where you want to have to go when the grid is down. And they're UL 1741 compliant. Underwriters Laboratories is the UL 1741 is the testing protocol used to verify compliance with IEEE 1547, which is the standard that says that your inverter has to have certain things that it does. And mainly it says that the inverter must disconnect from the utility if the utility goes down. And that's to prevent the inverter from applying a back feed to the grid when somebody may have to be doing some maintenance out there and they're counting on there not being any voltage on the line. And they have to deliver a very nice sine wave to the utility. And generally they deliver actually a slightly better sine wave than the utility itself does because the utility rotating machinery doesn't generate an absolute perfect sine wave. It comes pretty close, but it's not perfect. And the electronic generation of the sine wave by the inverter actually is a little bit better than the utility. So that's a good way to be compliant if you do an actually better job. And most of them have provisions for connecting a fossil fuel emergency backup generator as well if your batteries run out of power. But not everybody necessarily takes advantage of that. Most of the people I know who have battery backup systems haven't bothered to set them up so they can connect a fossil fuel generator. After all, the whole idea is to replace the fossil generator with solar. So that's the main battery backup grid-connected inverter. Now you notice I label in the title here as possible plural. That is, these inverters sometimes can be connected in parallel or tandem, however you want to say it, up to 8 of them in some cases or 10 in other cases. And there's also sometimes in different systems, there's more than one kind of an inverter, and we'll take a look at that as we go. So let's see if we can get into a system here. But before we decide what kind of a system to get into, let's look at what the options are. There's actually two. There are DC coupled systems and there are AC coupled systems. I'm not going to read all this because we got a couple of pictures coming up and I'm going to explain the diagrams instead. But you will have this backup information if you order the slides after the program is over to explain the pictures we're about to look at. Here we've got a DC coupled system. And exactly how does this work? Well, it starts with the PV array, which generates DC electricity. And usually you've got a bunch of source circuits, 4 to 8 to maybe more than 8. Typically, the source circuit's running up to no more than 150 volts DC, but with some systems they'll go to 600 or even 1,000. But assuming 150 volts, in order to get a lot of power, that means a lot of current. And since the individual modules typically don't deliver more than 10 amps each, if you want more than 10 amps, say 100 or 200 or 1,000, then you're going to have more parallel series of arrays of or strings of modules. And these are called source circuits. So, and we'll look at an actual circuit later on after the design, but we're looking at the block diagram, the functional diagram right now, so everybody can understand the intent of the system. So the source circuit combiner box is kind of like a backwards AC distribution panel, because the distribution panel, you know, you come in with the fat wires and then you distribute out with smaller wires to the individual branch circuits. Well, here you come in with the smaller wires, 10 amps each or so from the PV array, but as many as you need to get the power you need. And then you combine them in the source circuit combiner box. Maybe you can include a surge arrestor so that if you get lightning striking your array, the surge arrestor will protect the rest of your electronic equipment. After the source circuit combiner box, which will typically output somewhere 60 amps, 80 amps, something like that, goes to a charge controller. All right, and that charge controller has a lot of different functions in it, including, in particular, maximum power point tracking. And this is where it's almost like a DC to DC transformer. Let's say you've got 100 volts on the array and you want 52 volts for charging the batteries. Basically, the charge controller transforms down from the 100 to 52 in a DC to DC conversion type operation in order to charge the batteries. Once the batteries are charged, then that DC is available to the green AC battery backup inverter, which can then deliver energy to either the standby loads or the distribution panel, depending on whether the utility is in operation or not. If the utility should drop out, that connection to the distribution panel on the top right, the brown one, is disconnected by the battery backup inverter, and the inverter, the system of the array, source circuit combiner, charge controllers, batteries, and the battery backup inverter functions as a standalone photovoltaic system that provides AC power to the standby loads, which need to be designated. So that's the DC coupled system, all right? The other kind of system is the AC coupled system. Notice the difference here. The PV array goes directly to a direct grid connected inverter. Now, the direct grid connected inverter is a very finely tuned device. They've been making them for 20 or some odd years now, maybe more than 20 actually, and they're doing a really good job of it. And they are so good that they will convert almost at least 98% of the PV array energy into useful 120 volt, actually 120, 240 AC electricity. And that's fed directly to the standby loads in the standby load panel. And of course, we have to yet define those standby loads. And if there's wind or low head hydro or other similar electricity available that meets the UL 1741 generation requirement, then all these generators can be connected in parallel into the standby loads. And in addition, notice that notice the directions of the arrowheads here, folks, that the PV array transfers power only to the direct grid connecting inverter, which transfers power only to the standby loads. On the other hand, if the standby loads are met and there's extra electricity left over, then notice that double-headed arrow going over to the green battery backup inverter. That means that AC can go in either direction there. If the needs of the standby loads are met by the PV array and the direct grid connect inverter, then the leftover power goes to the battery backup inverter, which then has the option of using it to charge the batteries if they need it, or to simply send it up to the main distribution panel or wherever the point of utility connection might be, where it's used by whatever loads are there. And if there's still some left over, it goes to the utility. Okay, so pretty straightforward operation. The important thing is to notice the direction, the possible power flow directions, some cases in 2 directions, and some cases in only 1 direction. Now, the idea that these things are connected to the utility means the utility needs to know about it. They need to be happy with it, and therefore they are going to ask you to sit down with them and sign a utility interconnect agreement. But for the most part, that is not too terribly complex. Utilities are kind of getting used to it, even though because now so much of this is going on, they're beginning to like it less and less, because utilities, they kind of like to install the systems themselves. Now, there's some reasons why that might be good. There's some reasons why maybe it's not so good. One reason is quality control amongst the smaller solar installers. And that's one reason why we need to have the architects and engineers designing good systems that are going to run and operate properly and efficiently for many, many years. And unfortunately, that's not necessarily the thing that's always happening. We've seen some difficulties with that here in Florida. We are doing our best to fix that by convincing people that it is not good for anybody to design bad systems. All right. So there's the two block diagrams. Let's get down to business, and we're actually going to design in gory detail several systems this afternoon. And like I say, the calculations, everything are going to be here. Everything you need to show on a permit is going to be handled this afternoon, including wind load calculations. So in order to do that in 2 hours, that's not too easy. So the whole idea is that I want you to know how to do it, so that if you seriously want to get interested in becoming a part of this, if you're not already, that you can come back to these slides, and these will be your notes then for reviewing the material. And the reference book, it's also what the slides are based on, chapter 6 of the book that was published back in 2017. So we've got a few updates to them. All right, so let's look at the basics. First thing, it's a good idea to list everything you like to keep running in the event of utility outage, okay? And if you do that, there may be some monthly variations in some of these loads. Like you might have if you're up north, there might be a furnace fan motor that doesn't run all summer long, but it runs in the winter. But you may have some air conditioning that runs, or some fans that run in the summer. And probably you got more lighting load in the winter than in the summer, and so forth. So you may want to try to figure out which month is your worst month. And some people will do 12 months of analysis just to really be persnickety about it all. Some people will list a typical month. Some people will say, well, what I'm really interested in is making a certain amount of electricity during the year, and whatever's left over or whatever I can save, I'll run certain loads. So there are a lot of decisions to be made here. Depending on how much detail you want, it's possible to list 12 months of loads and estimate exactly how much might be used by anything that you'd like to be using in the event of utility outage. So now this is something you particularly would do with a standalone system, but not necessarily go into that much detail with a battery backup system. And you list the months when it's most likely you're going to need the battery backup power. Down here in Florida, September, October are more typical times that we're going to have, or maybe August, September, October is when hurricanes like to come and visit us. But up in New York and up New England and so forth, ice storms are not unusual, bringing down power lines. So this is for the engineer to figure out when it's most likely the utility will go down, if ever. Now, one thing we're going to notice is that the battery backup PV systems don't necessarily have to just be there if the utility goes down. They can be there to help reduce demand on the utility by providing battery power when the utility needs a little boost. Or if they want to charge you more money at a certain time of day, you can say, okay, I'll tell you what, I'm going to run my batteries then and run my loads off batteries rather than buying from the utility. So they're, in the modern day, these are not options that existed back in 2005 or 2000, but today, there are lots of other possible options you'll want to do with your backup power. And we'll talk about those as we go. So once you know what kind of backup power you're going to be using, then you have to figure out what kind of an inverter to use. And that's going to be based on the standby load voltage and the standby load power needs. Then you're going to have to estimate the battery capacity. You don't have to, but it's a good idea to, if you really want to know whether you can meet the demands of your standby loads or not. All right. And estimate now if the utility's down, once the batteries are drained, you got to fill them up again. So you need enough solar electricity to fill those batteries back up again. So we need to figure that out. And we need to sometimes, it's useful to determine what percentage of the energy needs for daily consumption are used during the day when the sun is shining, and how much of it is used at night when the sun is not shining. All right, and we're going to we'll take a really close look at that when we design an AC coupled system a little bit later on. All right, we need to decide whether we want an AC coupled or a DC coupled system. And we need to decide whether the system needs to be a three-phase system, because it's possible to have a three-phase battery backup system, using in some cases up to 9 inverters, 3 per phase. So the rules say you need to figure out what your standby loads might be. Notice I'm calling these standby loads rather than emergency loads. There's a very fine dividing line there. The National Fire Code says that if you want to have emergency power, it has to be fossil fueled power. Now, interestingly enough, the transition from utility to standby, if the utility is lost, in a AC or DC coupled photovoltaic system takes place in a few milliseconds, whereas a fossil generator, it can classify as an emergency load or emergency generator, even if you have to connect it manually and it takes you a couple hours to set it up. It can still be an emergency generator. So there are certain jurisdictions, and the code allows that if you want to claim that this photovoltaic battery backup system will provide emergency power, if you can convince your local authority having jurisdiction that this is actually a better option than some of the fossil options, they are allowed to go along with that deal. So we're going to call it standby, but it's conceivable that a local authority having jurisdiction might agree to it being emergency power. Okay, I'm going to stop for a minute. I see we've got 18 participants. That I guess includes me and PDH 16. Welcome to all of you. And what I need to know, since when I'm presenting here the PowerPoint, it uses up pretty much all of my screen except for my dialog box across the top. And when somebody has a question, presumably the Q&A icon lights up so that I will see that. So I would appreciate it if someone would just type in something like, does the box light up? So I can see whether my box lights up. Because if you have a question, I want to be able to address it and, okay, that box lit up. Okay, all right, great. No need to go any further. So when I see that little red light come up by my Q&A box, I guess I'm gonna have to answer that now, or else that red light's gonna stay on. Skyloo Local said test, and I'm gonna answer live. I just answered it live, okay. We're done with that, so it'll go away, I think. Okay, excellent. So now we know, everybody's aware. Just hit the Q&A if you have a question, and I shall do my best to respond as quickly as I can. And I know you may have attended webinars. I've attended several of them lately. This when an old 76-year-old guy's got nothing to do but stay home, you entertain yourself by taking some webinars from time to time. And when you take them that are national with 100 participants, there's no way you're going to get to say anything, and chances are your question won't be answered either. But with 18 participants and 16 or however we are going to answer questions today, ladies and gentlemen. So don't hesitate to ask. I used to always tell my students that you're not getting your money's worth if you don't answer questions, or ask questions, because that's part of what you're paying for, is to get your questions answered. And we shall do the best we can. Okay, looking at the load description here. This is fairly typical about what things people might like to be able to run during a power outage. Now, there's a whole lot of other stuff that might like to be run as well, But let's see what we can do if we have this small list of things: refrigerator, microwave oven, washing machine, computer, and so forth. You list the load, you look at the nameplate, what's the power use. Refrigerator nameplate is probably not going to say 144 watts. You're going to have to estimate that by the kilowatt hours per year divided by 12, divided by whatever, assuming the duty cycle. And a reasonable number is somewhere around 150 watts for a modern refrigerator. Microwave ovens are about 900 watts. So we'll connect the refrigerator line 1. That's going to take 1.5 amps. If we multiply the volts times the amps, 120 volts, times 1.5 amps, times the number of hours a day, we get the kilowatt hours a day for the refrigerator. Okay. Microwave oven, 7.5 amps, 900 watts. If it were 1,000 watts, we ran it for an hour, it would use a kilowatt hour a day. So we're assuming we're going to run this thing somewhere around 6/10 of an hour in a day's time. It's our only cooking, and we're probably heating up some hot dogs or soup or something. Anyway, these are all numbers that you use your judgment on. Okay, I mean, if you don't like the number, you put a different number and you see what you end up with at the bottom of the page, and then you see if you can design to that number. All right, so these are estimates, and these are what our ultimately designed system will produce if we do it right. Okay, and if we're not happy with the amount of power we're getting, then we may need a bigger system, but that's all right. That's what design is all about. You try it. If you don't like it, you go back to the drawing board. Okay, so you notice we bounce them back and forth, line 1 to line 2, balance them as closely as possible. We don't have a perfect balance. 16 amps on line 1, 12.9 on line 2. If they're all running at the same time, but we're going to discover that that's not a very good idea either, because the batteries are not happy if you turn on everything all at the same time. But why do you have to run your, say, the microwave oven and the washing machine at the same time? Let's trade off. And if you got an emergency thing, you can certainly turn off the washing machine while you run the microwave oven. All right, so here's some loads. Let's see what we can design around these now, all right? Let's start by selecting the inverter. It has to be able to pass through 3,424 watts at 12240 volts, okay? It has to pass through at least 16 amps. Now, pass through means from the utility to the load, okay? It also means it has to be able to generate that from the batteries if necessary, okay? So 120, and then this is 16 amps as a maximum load. The load on line 2 is less than that, so we're mainly concerned about meeting the requirements on line 1. If we can do that, we'll also be able to meet the requirements on line 2. So if we could find a 12240 volt inverter, in other words, line 1, line 2, and neutral, that will pass through 50 amps when the grid is operational and will supply a mere 16 when the grid is down, it'll work. So the 50 amps is an extra bonus. We could have some extra loads on that panel, but we wouldn't be able to run them in the event that the utility is down, okay? So the inverter will likely use 48 volt battery pack, all right? And it probably is going to need external ground fault detection and interruption and arc fault circuit interruption and maximum power point tracking. But we just discussed that. And those are external boxes, and they get connected through a DC component enclosure on the DC side of the inverter. Unless, of course, the DCs are all combined as within the inverter, and we'll see one of those later on. This never was the case way back in 2005, but now somebody actually makes these with everything in the same box. So that makes it a whole lot simpler. The inverter needs to be capable of charging batteries from the grid if the array is down. Okay, that's a given. That's generally the inverters do that. I don't know of any that don't. The inverter may use external DC and AC component enclosures. Yeah, a lot of them do. They're generally sold by the same manufacturer, fit on a nice backboard or nice mounting. The standby circuits sometimes are run right out at the AC enclosure, or sometimes the AC enclosure will feed a sub-panel with standby circuits. It's all a matter up to the designer to decide what's easier to do within the specific occupancy. Maybe you've got the refrigerator, microwave, and some lighting circuits that go into a main distribution panel. You run an extra conduit in there, a bunch of wires down there, you pull those wires off the breaker so that you're basically using that panel as a junction box. As long as you don't crowd it too badly in there, most local jurisdictions will say, all right, we'll let you get by with that. We understand what you're doing. It's actually taking the load off the bus bar, so that's a good thing. Okay. And the charging set points, you know, how many volts do you set the charger to? Depends on battery technology, so that these are programmable by the user, and sometimes you have to be a little careful about that. We're going to talk about some typical set points, but just a reminder that these are things that the designer and installer needs to pay attention to. All right, so let's look at two models of inverter. And these are features, and I don't want to read this whole thing. They do a lot of nice things. Let's look instead. You can read this when you order up the slides. I'd rather talk about the design process. But here's some of the technical specs, okay? This is a family of two inverters. One is rated at basically 4,000 watts, another's rated at 8,000 watts. We'll call them volt amps because the volts and the amps don't necessarily have to be in phase. If they run a motor, for example, they can run motors. So the 4,000 volt amp unit, for surge power, it'll give you 5 seconds, it'll give you 6,000 volt amperes. And in 100 milliseconds time, it'll give you 8,500 volt amperes. Well, that's surely enough to start a 1 horsepower motor, for example, at 120 volts, or certainly enough to start out a 1 horsepower motor, maybe even bigger one, at 240 volts. The peak power for 30 minutes, you can get 4,500 volt amps out. At 25 degrees C, you can run it forever at 4,000 watts. More than likely, you're not going to want to do that because it would take a huge battery pack to continuously deliver 4,000 watts to your loads. But if that's what you want to do, then that's what you do. DC input from 40 to 64, that's nice because that means that if you want to go with lithium or lead acid or maybe some other alternatives, that range is pretty broad and it will adapt to a wide range of different battery technologies. You notice the 8,000 volt amp unit to the right of it is just like 2 of these in one package because it does double everything. We got the possible continuous AC output current of 16.7 amps. We needed 16, so we've just barely made it here. But again, we're not going to run 16.7 amps continuously anyway. Maximum AC input current 50 amps. Gee whiz, that just happens to be what we wrote down. You'd almost think we knew about this inverter ahead of time. DC input current at rated volt ampere output, 92 amps. Okay, but that's that rated output. You want to size your cables and your circuit breakers for the surge current though. So you're probably going to set it up for a lot more current than that. And it will continuously charge your batteries at 57.5 amps. And the California Energy Commission weighted efficiency of this unit happens to be 92.5%. And this is the downside of this particular inverter. You're losing 7.5% to the inverter. So that means 7.5% extra energy you need to supply from the battery. So I need to keep that in mind. Okay. Oh, I clicked my little wheel. I didn't mean to do that. Okay, I think we have some questions. Let's see what we got here. Can we design including a heat pump? The answer is sure. You just need to decide how big of a heat pump. If it's a mini split, for example, That's almost as low as 5,000 watts. So you look at the volt amperes on your heat pump, whether it's a water cooled or air cooled, it doesn't make any difference. It's just electricity we're talking about. And that's part of the reason why the instantaneous power and the surge power is so high on these things, so that it will start the motor and it'll start a compressor. Not a problem. So for this particular system we're looking at here, you probably wouldn't want your heat pump to be more than, say, 1.5 tons. If you had a bigger heat pump, you'd probably want a bigger system. Okay, so we answered that one live. Click that and click my done. And okay, if that didn't answer the question, feel free to comment back again. Okay, so the only downside of this particular inverter is the efficiency. It's 92.5% of the DC that you put in will come out as AC. So that means extra storage necessary in the batteries and so forth. Okay, but clearly the 4,000 volt amp unit will meet the performance specs that we listed on the previous page. So now we need to choose the batteries. Daily load requirements for 7.65 kilowatt hours. That's what we start with. Okay, and that comes from our load specification. So that means clearly this is 7.65 kilowatt hours that need to be provided to the loads by the inverter. Okay, so that means using 94% inverter efficiency and a little bit of inefficiency in the wiring, say another 2% loss, we divide that 7.65 at the inverter output to get what we need at the input to the inverter. And that means we have to supply the inverter with 8.3 kilowatt hours in order for it to provide 7.65 kilowatt hours. Okay, it's important to run this little calculation, and as you see these things, you'll probably notice that if you build a spreadsheet, it will do this stuff for you while you're taking a sip of coffee. All right, so if you get into this stuff seriously, you're going to want to build yourself an Excel spreadsheet that just does this all. You just tell it, you spend your time making your load requirements, and after which you do that, you can put equipment in with equipment specs, and it'll help you pick the equipment and all sorts of nice things. So we're going to do this the hard way by hand, but we're also going to explain every step of the way what we're doing to the extent possible within reason, to not go grossly over time and miss out on any evening television. Okay, so the amp hours from the batteries then will be the watt hours divided by the voltage. So 8.3 kilowatt hours is 8,300 watt hours. If I divide that by the battery voltage, that means I need 172.9 amp hours out of the battery to the inverter. That doesn't mean, in order to get 172.9 amp hours out of the batteries, I got to put more than that in, because there is a round trip inefficiency of about 10% for lead acid batteries and about 4 to 5% for lithium batteries. So we need to account for that. Okay, so if we allow 80% depth of discharge, and again, that's a lead acid thing, but it's also not a bad idea with lithium. With lithium, they say, and presumably you can discharge you 100%, but if you do that, the voltage goes way down. At 80% discharge lithium batteries, if you start going more than that, the battery voltage starts dropping off fairly quickly. And so normally you don't want to do that either. So regardless of your battery technology with the currently available technologies, it's a good idea to design for using 80% of the available charge in the battery. So that means the battery itself needs 216 amp hours in order to provide 172.9 to the inverter. Okay, so 216 amp hour batteries, and usually we're going to we want to save enough electricity for a whole day. So the charging rate or the discharging rate is equal to the number of hours, it is just expressed as the number of hours it takes to discharge. So C divided by 24 means it's 24-hour discharge. When you look at the specifications on a lead acid deep cycle battery or any deep cycle battery of any technology, they will normally give you how many amp hours you can get depending on the rate of discharge. And the slower you discharge, the more amp hours you can get out that will be useful for the battery. And there's a very simple reason for that. The battery has internal resistance. And when current goes through a resistance, the power dissipation in that resistance is proportional to the square of the current. So as you discharge twice as fast, you lose 4 times as much power internally to the batteries, which means that's less power available for the loads themselves. So that's why at a C24 discharge rate, you can get more kilowatt hours out of the battery or more amp hours out of the battery than if you discharge it in 12 hours or 4 hours or 6 hours. And for lead acid, you generally don't want to discharge at a rate of more than 5 hours. If you discharge in less than 5 hours, you can actually damage the batteries. So you tend not to want to do that. For lithium batteries, they've got a lot smaller internal resistance, and you have to look at the battery specs, but sometimes they can be discharged in an hour, hour and a half, and not damage the battery pack. So that's something to look at. We'll come to that in a minute. You look for deep discharge batteries because there's 2 different kinds. There's deep discharge that are used for storage and for energy. But the kind you use to start your automobile is a shallow discharge. The difference, deep discharge have thicker lead plates with smaller area. The batteries that start your automobile have much more area of the lead plates, but they're thinner, and they are not designed to deliver more than 20% of the total energy in the battery. But normally you don't need to do that to get the car started. All right, AGM is just absorbent glass mat. It's a sealed battery, and you can run it upside down, sideways, in any direction you want, and it's maintenance free. It's more expensive than flooded batteries, but it's a real bother to have to mess with the batteries and make sure that they're filled with water. Everybody knows that who has had to worry about an automobile battery. Okay. It turns out that 216 amps at 6 volts is a pretty common size for a number of battery manufacturers. So why not put 8 of these in series, and 6 times 8 is 48 volts. So that gives you 216 amp hours at 48 volts, which is exactly what we're looking for, which gives you the number of watt hours that you need to meet your daily load requirements of 7.65 kilowatt hours. So there we got it. Just like that, 1 page on a PowerPoint slide and your batteries are selected. Isn't that fantastic? All right, for lithium battery, you just have to check the voltage. Some of the battery lithium packs are lower than 48 volts, but generally almost always more than 40. And what are the kilowatt hour ratings? There's one final check here. Oh, I lied, didn't I? I said we designed the batteries with just 1 slide, but we're going to use 2 just to make sure here. Because we've been designing using the energy requirements from the battery. Let's look at the power requirements, okay? If we take 24 hours to discharge these batteries, it means the discharge rate would be 345.6 watts continuously for 24 hours. But that's not the way we're going to run this system. We're going to use more than that some of the time and less than that some of the time. But we'd rather not discharge in less than 5 hours. So in order to make sure of that, it would be good if we tried to limit the discharge rate of the batteries to 1,660 watts for 5 hours. Now that doesn't mean we can't do 3,000 watts for 20 minutes, all right, and then back off to other smaller amounts. But it turns out that in fact, with the loads that we've listed at the beginning, you can hardly notice the difference if you use those. Okay, I don't know if you can hear my phone ringing. It's a wireless caller. They're probably just asking for money. Let's see if we can turn that off somehow. Okay, so it's just a good idea to maximize the amount of energy you get from batteries to not run all your loads at the same time. It's just simple. If you can do that manually one way or another, you get a lot more performance out of the batteries. And if you can't, maybe you need to put in another string of batteries and have twice as much, or some smaller ones and have 1.5 times as much or something. Okay, and the other point here is lithium, because of the lower internal resistance, you can discharge it faster. Okay, so we got the inverter, we got the batteries, now we've got the array. How do we do that? All right, well, we know the batteries need 8.3 kilowatt hours a day delivered. Okay, it means that in order to deliver 8.3 kilowatt hours, they're going to lose 10% round trip. So if we put in a certain amount, we get, if we want 8.3 out, we need more in. And so we just divide the 8.3 by 0.9 and 90% round trip efficiency. That means we need to provide the batteries themselves with 9.22 kilowatt hours a day. Okay, and where's that coming from? That's coming from the solar array. All right, so you look at the array and what might the losses be? Well, when it gets hot, the array loses power and you maybe only get you may lose 15% of the performance. Maybe it's a little dusty, maybe some wiring losses, maybe some losses in the maximum power point charge controller. But guess what? It doesn't make any difference whether you're running a battery backup system or whether you're running a straight grid connect system. The amount of energy available at the output of the maximum power point tracking charge control is going to be the same as the amount of energy out of a straight grid connect inverter, because the efficiencies of the charge controller is about the same as the efficiency of the straight grid connect inverter. And what that does for us, it lets us use the National Renewable Energy Lab's system advisory model to analyze how much of an array we need in order to get the number of kilowatt hours we need in a year's time to meet the needs of our load. Okay? So, NREL SAM, nice complementary analysis tool from National Renewable Energy Lab. Just Google NREL SAM, and there it is for download for free. And you just need to give them your email address, a little more information, because after all, we paid for it with our tax dollar. They want to be able to justify that a lot of us are using it. So they need to be able to tell how many people they've shared their output with. Now, NREL SAM is not the only one available. You can pay real money too, $1,000 or so for an analysis program that maybe has more weather data, more localized weather data, whatever. But SAM's a pretty good start. It is a very nice program. Okay, and we're going to show some results a little bit later. If we happen to want to locate this thing in Tampa with a roof slope of 18.43 degrees, that's a 412 slope, I think, then we would want 9.22 kilowatt hours every day, okay, or 286 kilowatt hours in a 31-day month. All right, that's to meet the 9.22 kilowatt hours to the battery requirement, okay? So what do we do to get that? Well, we can start with a 1 kW array, okay? And if we crank in that we have a 1 kilowatt array in Tampa, looking south at 18.43 degree tilt, then this will give us, according to SAM, 1,475 kilowatt hours a year. And it breaks it down by month. August, we'll get 134. September, we get 119. October, 121. So now we decide, okay, we would like 286 kilowatt hours. And in Tampa, we're going to design this thing for a September hurricane. So we want to make sure that instead of 119 kilowatt hours in September, we get 286 kilowatt hours. So how do we get that? Well, we simply multiply by 286 over 119. Okay? And if we do that, that's a factor of 2.401. So instead of 1 kW array, we just need a 2.4 kW array. Now, wow, you know, I mean, this is just multiplication and division kinds of arithmetic, a little bit of addition once in a while. You got to promise me, don't tell anybody how simple this is, okay? Because here we go, we got 2.4 kW array. And if we do that, we're going to get 3,543 kilowatt hours a year, 322 in August, 286 in September, and 290 in October. All right, so that means September, October, we're good. Okay, because we'll meet our 286 kilowatt hour minimum. Will this happen all year long? What if something happens? What if Tampa, what if they get a terrible ice storm in December or November? Will they still be able to, or an unseasonable something? Well, if we wanted to have that 9.22 every day, every month, and you know, this is on average anyway, there will be some days where the sun don't do that for you, but hurricane-wise, typically the day after a hurricane, it's clear and sunny, and the only reason you know there was a hurricane is because everything's all blown to bits. So the array that we have works fine as August, September, and October, but January, February, November, and December, it will not deliver 9.22 kilowatt hours a day according to the NREL SAM model. So if we want 9.22 kilowatt hours a day every month, then the December production would be 222 with the 2.4 kW array. Is that what we came up with? And we need to bump that up from 222 to 286. That means we're going to bump up every month, which means we're going to have more electricity than we need some of those months, which means if the utility is up, that's fine. We then just sell it to the utility, or it's used in other loads if we meet the needs of all of our standby loads. So what size array would give us every day of the year, or every month of the year at least, on average, at least 9.2 kilowatt hours a day? Well, we just up it by 286 over 222, which is 1.29. So we take that previous array size and multiply by 1.29, and we're up to a 3.1 kW array. Okay? So, so far so good. Now that 3.1 kW array, remember, that has to feed into that charge controller that controls the battery. So we need now to take a look at the charge controller and make sure that it can handle 3.1 kW array. So that will be our next step, is looking at the charge controller. But also, how do we get 3.1 kW array? We need to take a look at how we might do that as well. So, in any case, this will give us 4,570 kilowatt hours to the batteries, 286 in December as the lowest month. And in April, you get 449 kilowatt hours as the maximum, and all that you need in those hurricane months, okay? So that's what you get if you do this, is install a 3.1 kW array. All right, somebody's saying, how much will it take to charge an electric car? Well, it turns out, depending on how much you drive, typically about 1.5 kW added to that 3.1 will keep your electric car charged for about 50 miles a day. So I think about 50, I don't know, I did that calculation a little while back, but it's not a difficult calculation. If you get roughly 3.5 miles per kilowatt hour, which is fairly typical, using that, you can determine how many kilowatt hours you need per day, per week, per month to drive your electric vehicle. So, and that I say that because this is going to be a big thing over the next 10 years. Mark my words. I mean, we are driving a plug-in hybrid We are getting over 500 miles to the gallon because mostly we drive at less than 20 miles a day, and it runs on electricity, period. So it is coming here. It is a wonderful automobile. Never had one so good. Okay, I'm getting off base here. So what are the constraints on the array? Well, charge controller maximum output power for a particular 60 amp charge controller is 3,200 watts. All right, so if the array is much bigger than 3,200 watts, the charge controller may not be able to handle it all. On the other hand, we have to recognize that the array itself, if it's rated at 3,200 watts, almost never does it actually generate 3,200 watts. For a number of reasons, particularly in Tampa, the array will almost always run hotter than 25 degrees C. And when it runs hotter than 25 degrees C, there is a temperature degradation. And so it therefore will not put out its rated power. Furthermore, if the sun is not directly striking that array, if it's striking it at an angle, you have a little cosine function involved, which further reduces the output. So the array power can actually be more than 3,200 watts, the rating, because it's almost never going to deliver its rated power. And if you're wondering about that, nice thing about NREL SAM is it gives you a hour by hour annual analysis of array of system output power. And you can just look across that, what is it, 8,620 hours in a year, something like that. Look through those 8,620 hours and you'll see that for a 3,200 watt array, probably it's never going to give out much more than 2,900 and only for a short amount of time. Okay, just useful things to know when you're designing these things. You don't have to guess at it. You can look up the things on the simulations. A lot of charge controllers have maximum input voltages of 150 volts. What I'm looking at is a particular charge controller here, and we want to see if we can use this one in the system. See, we could go 15% above 3,200 watts and we'd still be okay. Charge controller output is limited to about 260 amps, period. The open circuit voltage of the array has to be less than 150 volts. We need to take that into account because the colder the array gets, like on a cold winter morning in Vermont or New York, we have to make sure that those modules don't run at more than 150 volts when it starts up in the morning, okay? And the maximum power voltage of the array should generally be more than 65 volts also, just to optimize the maximum power point tracking of the charge controller, okay? So just some numbers to keep in mind. And if you keep the array voltage in this range, then you don't need to worry much about whether you're making the charge controller happy. It's preferable to keep the array standard or STC power, standard test condition power, somewhere between 2,800 and 3,600 watts. That's our bottom line. And so therefore, that's for the charge controller. And since we're suggesting a 3.1 kW array, that means this charge controller just happens to be perfect. And when you get to know your charge controllers, you kind of know which one is going to be perfect for your array, and you don't have to do a whole lot of guessing. But you can understand the iterative process. You look through a bunch of specs. Fortunately, the spec sheets on all these things are 2 pages long. The inverter gives you 2 pages of specs that gives you essentially everything you need to know except how to hook it up. But it gives you all the performance information. It's possible to use larger charge controllers. It's possible to use more than one charge controller in parallel. So, and sometimes you want to do that anyway, because if you have one part of the array looking in one direction and another part looking in another direction, they will require separate and distinct maximum power point tracking anyway, because the 2 arrays will not be having the exact same maximum power conditions, and you don't want to mix those up. Okay, looking at some possible module choices. These are some real world 2018, 2020 variety modules. a 235 watt module, 320 watt module, 265, 300. And what this gives you is the performance parameters of the modules. VOC is the open circuit voltage. That's if you don't connect it to anything. That's the open circuit voltage at 25 degrees C. Notice the B module has a much bigger open circuit voltage, 64.8. That's because that's a 72 cell module rather than the others are 60 cell modules. Okay. Short circuit current is if you take those two leads of the module and short them together, which you can do, by the way, without damaging the module or the person shorting the leads together. You'd get 8.48 amps. Or with B, you get 6.24 and so forth. Maximum power voltage is the voltage that module operates at 25 degrees C and gives you the maximum power out. And the maximum power current is the maximum power current that you get at the maximum power voltage operation at 25 degrees C. And the two right-hand columns show you the temperature dependence of the open circuit voltage and the maximum power voltage. Okay, and you see they're both negative temperature coefficients, meaning the hotter they get, the more they lose power. Okay, so the reason these are important is because it makes it very easy to calculate, knowing what the weather conditions are at the site of the installation, what's the highest voltage is going to ever reach for a particular module. So let's take a look at it and see what we get. Whoops, the question seems to be up. Let's go to the Q&A. Hold on. 8.3 kilowatt hour a day, taking into account 80% efficiency. It takes, let's see, 8.3 kilowatt hour a day. I need to back up and get my mind around this part of it. No, we don't. The array, there's no round trip involved with the array, okay? It's just a one-way. Electricity is made at the array and it goes down to the battery. So there's no additional efficiency thing, and all of those losses are taken into account in the NREL SAM analysis. Okay, so that's the answer to that one. And does the NREL SAM allow you to do LOLP analysis? You know what? I've never done that on SAM. I guess I'm not exactly sure. I mean, when you talk about LOLP in a transmission situation, the loss of load probability goes a whole lot higher when you come closer to the maximum load of the system. From a photovoltaic standpoint, it doesn't care whether you're running it open circuit or whether you're running it full load. The loss of load probability is the same. So it's a little bit different from an AC system if that's what you're asking. Okay, now let's see. 8.3, now we're getting lots of questions. Let me get up to the top here. You need size of the array with another, okay, no, you don't need another 10% on the round trip efficiency. 8.3 kilowatt hour a day takes into account. What it takes into account, I have to go back to the slide on that one because I don't remember where the 8.3 kilowatt hours was. The first thing we need is you know what you need to your loads, and then you need to take into account the inverter efficiency to determine how much you need to the inverter. And then you need to take into account what you need to the batteries. That's your 10% round trip efficiency, okay? Because you only get out 90% of what you put in. You lose the other 10% to heating by the internal resistance of the batteries. And then the 80% number that I used was simply, we want to leave 20% of the battery capacity in the battery, but we don't want to drain it to 100% or down to zero. So that's why we divide by that extra 0.8 to get up to the 216 amp hours. I hope that answers that question without having to go back to that slide. Let's see, is there a main driving force when deciding between AC versus DC system? And kind of yes, and we're going to come to an AC system pretty soon. Let's see, what time is it here? 309, 310, yeah, we'll get there. Is there, and let's see, oh, thanks, okay, you're welcome. And if you are limited with how big, of an array you can install, does the NREL SAM allow you to do loss of load probability analysis? And I don't, if you're talking about the kind of LOLP that's done with utilities, the PV kind of LOLP is a little bit different. I guess what you're talking, it's not really loss of load probability. It's more of a loss of source probability. Well, it's the same thing, I guess, because if your load gets too high, it's more likely you're going to lose your generation. You could do that manually if you're, I think what you're maybe saying is, what on a given cloudy day will you only be able to use, you certainly won't be able to use all of your loads on a day that's well below the design value. And so you can't do that on a day-by-day predictable analysis any more than you can predict the weather 3 weeks from now, exactly what it's going to be on any particular day. The NREL SAM uses a typical meteorological year, which does take into account temperature, cloud cover, and so forth on an average typical kind of a situation. I'm not sure whether we're ever going to have a typical year again, but in any case, that's what they're limited to. So I'm not quite sure. Oh, okay, here we go. Kenneth, LOLP, if you would add an additional load to a system past the original design and cannot add to the battery system or increase the array size, okay, can you estimate probability of load loss? In other words, what you're defining LOLP here is draining the batteries all the way, which if that happens, by the way, the inverter will shut down, and that's programmable where it shuts down to protect the batteries. And the answer is, yeah, you can estimate that, yeah, sure. And in fact, you can put additional controls in the system that will shut down certain loads as the battery voltage starts going down to try to avoid that kind of a situation. So I guess the answer, Kenneth, in that case is, yeah, you can do that kind of an estimate. And I hope that I finally hopefully got that straight. Let's see, live answer, done, live answer, okay, we're going to talk to that in a minute. Okay, Alex, let's see, small remote off-grid cabin, 12-volt loads. We use a charge controller to charge batteries, then attach load directly to batteries. Better use an inverter that offers 12-volt output. Attach the load to the inverter. You know, there's so many different possibilities here, Alex, that I mean, this is pretty rare now to use only 12-volt loads because inverters are so cheap, so dependable, and it takes such fat wire to run 12-volt loads that almost nobody runs an off-grid cabin on 12-volt loads anymore. But if this were the case, you know what, I'm going to tell you there is an answer to this question. If you find the reference book on the website, there's an incomplete chapter on off-grid PV designs. And they were a lot more complex than anything we're doing here today. And I just don't have the time to go into detail here. I wish I could, because personally, I would connect an inverter, say use 120 volt output and wire for 120 volts, because technically speaking, the National Electrical Code requires you to wire that cabin now for 120 volts anyway. So that's the best I can do on this one. And let's see, load system. Okay, and we got that one. Okay. All right. You know, I really appreciate the questions. For one, it helps me a lot to get the questions, so keep them coming. All right, temperature corrections. A quick calculation here for the modules, okay? And what we're trying to figure out is to limit the voltage to 150 volts, okay? The maximum source circuit voltage with module A. If we use, see, we have to limit it to 150 volts, and we can't connect 3.7 modules in series. It's either 3 or 4. So we're limited to 3 of module A, and that'll give us 122.5. And if we have 3 of those modules, that's 705 watts in a source circuit, okay? That's what we're doing here. Maximum number of series modules of B, remember that's the bigger one, bigger open circuit module. So we can only put 2 of those in the circuit. All right, and that's 320, 640 watts total. Module C, we can only put 3. We get 795 watts if we do that. In module 4, with 3 of them in a circuit, source circuit, we can get 900 watts, okay? So module D, knowing that we want, and the module C look kind of like they might do the jobs, especially since module C is highlighted in red, because we're looking for 3,100 watts. And if we string 4 of those in parallel, that's pretty close to 3,100 watts, isn't it? If we have 10 B modules and 5 source circuits, we get 3,200 watt array. 12 C modules gives us a 3,180 watt array. And so either one of those works, and for that matter, even the D module will work, because 4 of those is 3,600 watts, and that's the outside of how much we're going to allow this array to have. So the next step then is just look at the roof and see which ones fit best, and the availability and the price per watt, and whether you like the supplier and things like that. But basically, that's what we're looking at. All right, so again, I promise you we're going to just do the whole design, and that includes the wire sizing. We're going to do it kind of quickly, though. And here's the rules, okay? We look at the short circuit current, because the wire sizing is based on the short circuit current. We have 4 source circuits, so the output current is the combination of the source circuits. So 4 times 9.2 is 36.8, okay? Most of the time, that amount of current is not going to flow, because that's not the maximum power current. The maximum power current is only about 80% of that. But we have to design at the short circuit current in case something shorts out, we don't have anything to burn up. All right, so National Electrical Code says, all right, for starters, take 156% of the short circuit current and write that down. All right, there you go, 14.4. PV output circuit, well, that's 57.4 because it's 4 times that, okay? The wire size to handle 14.4 amps, well, number 14 will handle it. So if you use number 10, that'll certainly do the job. But then again, it's warm up there. So we need to do a temperature D rate of 0.71 because it's warm on the up on the roof. And again, this is National Electrical Code. You need to go through and look these D rates up. There's conduit fill. We've got 4 source circuits coming down the conduit, so we got 8 conductors, and so we need to derate by 0.7. So even though the number 10 starts at 40 amps, it's only rated at 23.1. All right, on the other hand, we can use a 15 amp circuit breaker because 156% of that is 14.4 amps. Okay, now, if this derated ampacity happened to be less than 14.4, then we could take we have to take the larger of either 156% of the short circuit current or the derated ampacity. Okay, so if this thing were perfectly shaded and no derates, then a derated ampacity. If it's less than 14.4, then the wire would have to be rated at 14.4. Again, this is in section 690 of the National Electrical Code, spelled out pretty clearly. Same deal on the output circuit, except 4 times as much. But here it's different because the temperature derate and the conduit derate are 1 because there's only 2 wires and it's at ground level, no temperature, no conduit fill thing. So therefore, we just have to argue that 30-degree ampacity of number 6, we have to take 80% of that for continuous, and that's 57.4, okay? So note number 1 is based on selection of module C. And note number 2, where's note number 1? I believe I have a typo here, no matter how many times you go through this thing. Note number 2 is a larger, okay, that's what I was talking about. And yeah, this is, there's note number 1, it's up there, output wire sizing based on selection of module C. Okay, and again, can't go over any more detail here other than to tell you this is in the National Electrical Code section 690. Okay, now 12 and 14 meet the ampacity requirements, but they don't necessarily meet the derated ampacity requirements, and they may not meet voltage drop requirements. So the next thing we look at is voltage drop, okay? And here's all the circuits in the system. The charge controller output circuit, it's a 60 amp charge controller. You have to size the wire based on that. So we get number 6 wire with an 80 amp circuit breaker. The inverter DC input, 5-second surge current, 125 amps. 156 amps is 125% of that. That's not exactly continuous duty, but anyway, it's a good idea to minimize the voltage drop at 48 volts. Normally, 2-aught wire is used with a 175 amp breaker in order to, as the battery cables. Inverter AC input, 50 amps. AC output, 50 amps. This again is utility without when the utility is up. So again, using number 6 wire with 60 amp breakers. Okay. Voltage drop calculations for every circuit in the entire system. And there's a standard formula for calculating voltage drop. We'll see that in the next example. So I'm just going to show this slide. And again, it's a straightforward procedure to figure out whether your wire needs to be bigger to keep your voltage drop below 2%. Okay. Laying it out on the roof, we've got 4 source circuits with 3 modules each. They fit on this roof very nicely, assuming that this is what the roof looks like. It's probably going to look like this. This is for a wind load analysis. Notice we have 1, 2, 3, 4, 5, 6, 12 mounting points for 6 modules. Let's look at the math on that. We're urban, wind load exposure B, roof slope 18.43, mean roof height 15 feet. This all comes out of, by the way, ASCE 7. So American Society of Civil Engineers, publication 7, just like NFPA 90, that National Electrical Code. Every solar designer needs to have those 2 handbooks sitting on their desk. Okay. 140 mile per hour design speed in a category 2 building in Tampa. Again, that's out of the ASCE 7. And you find the wind speeds are downward 20.3 PSF and upward or suction pressure 32.3 PSF. All right. And since the module of each area of each module is 17.5 square feet, 6 of them is 105 square feet. We've got 32.3 pounds per square foot. We need to support 3,392 pounds of uplift. That's for the number of brackets we've got there. That's 283 pounds. Again, I'm just going through this kind of quickly. You can go through it again if you order the slides and get the details. If you use a 5/16 flag screw in Southern Pine, That has a pull strength of 332 pounds per inch, so therefore we only need to embed 0.85 inches into the trusses, though, folks, not into a piece of plywood. You can't embed 0.85 inches into a piece of 5/8 inch plywood. All right, so you got to go into the trusses. That's an absolute requirement. And since the rest of your system is warranted for 25 years, you better use stainless steel lag screws. Otherwise, they're going to rust out on you. It's going to look like the devil. All right, so the standby load distribution panel, let's look at it quickly. 120 volt panel, need at least 8 pole spaces plus a main breaker coming in. The 2-wire branch circuits, you can move them by just moving the hot and the neutral, and you're going to move a ground, of course. The 120 240s or just a 240, you need both of the line connections plus the neutral because you're going to use a 2-pole breaker. Multi-wire branch circuits, you can't move just one. If you got a multi-wire branch circuit in a main panel, you got to pull out both phases plus the neutral and terminate them on a 2-pole circuit breaker in the standby panel. So even if you didn't want to use one of those bedrooms, for example, that's where you typically have a multi-wire branch circuit. Question. Let's take a look. Oh, miss how I got the short circuit rating. It comes from the module specification sheet. Okay? Just that simple. All that data that we had in that little table came from the modules, the 2-page module specification sheets on those 4 modules. Okay? Okay, continuing on. When the grid is on, you can supply 48 amps. That's 80% of a 60 amp circuit breaker, okay? And the inverter's rated at continuous 50 amps, but this circuit breaker limits you to 48 amps, but still that's more than enough. So if you had additional loads on that panel, you'd probably just want to switch them down. You also might have to have the panel size bigger, okay? 16.7 amps per phase is available for standby from the inverter. We already know that. There's an inverter bypass switch, and we're going to see that in a minute in the schematic. And you may need to upgrade the standby circuit. Sometimes if you don't have GFCI or AFCI for your bedroom or kitchen or garage circuits or outdoor circuits, the local inspector will say, well, you're changing these, so you have to put a ground fault on it now. You didn't have one in that old house, but now you got to put the ground fault. So keep that in mind so the inspector doesn't knock you down for something they know something about, like AFCI and GFCI. More than likely, they'll pass the PV, or they'll, from what I'm hearing from friends in the business, they will fail it because of some simple thing, whereas there may be some major complex fault, but if they don't understand it, they'll miss it, and that's not fair. We don't want that to happen either. Here's some multi-wire branch circuits, just everybody's familiar. I'm not going to go detail, but remember the neutral current is equal to the difference between the line currents for 120 240 volt loads. So if the line currents are balanced, there is no neutral current. And the same is true difference on a 3-phase load. The neutral current is the sum of the line currents, but the line currents are 120 degrees out of phase. So if I got 10 amps for I3, 10 for I1, and 10 amps for I2, 10 plus 10 plus 10 equals 0. Interestingly enough, and I can't go into any detail here on that, but the maximum neutral current is going to be the maximum branch circuit current, which would be, for example, if there were some I1 and no I2 or no I3, then all of I1 would return on the neutral. Okay, grounding and bonding, NEC 250. I'm just going to click through this in a hurry. The rules are all clear, well spelled out. So here's our schematic. Notice the 12 modules. Notice the way they're wired. Interesting the way to wire them. The reason for doing that is to minimize the amount of extension cables needed. The leads on the modules themselves will allow you to go from that minus lead of module number 1 in the upper left-hand corner over to module 3 plus. And then module 3 minus goes to module 2 plus. Module 2 plus goes down to back to the junction box. So we got series connection of 3 modules with almost no additional. This is all open wiring with type USE2 or type PV. Normally it's type PV wire that's used in the module leads. And we have 4 source circuits coming down from the roof, source circuit combiner box, 4 15 amp circuit fuses in the combiner box, maybe 14 15 amp, or maybe 4 15 amp circuit breakers. 15 amp DC circuit breakers are relatively inexpensive, and most of the combiner boxes use DC circuit breakers. From there, it goes to the ground fault detection and interruption device, which if there's some ground fault in the circuits on the way down from the roof, that will trip out and shut off the power to the charge controller. There's a 60 amp circuit breaker at the charge controller input. There's an 80 amp circuit breaker at the charge controller output. The charge controller output is limited to 60, but it could be 60 continuous. So we need that 80 amp at 125% of 60 in order to handle that. That goes into the battery, the common terminal, and it charges the batteries if necessary from the charge controller. Or once the batteries are charged up to a high enough voltage, then it feeds the inverter, and the inverter converts it to AC. The AC goes to the AC component enclosure, and here's that bypass, inverter bypass we were talking about. If you look at the distribution panel, we've got AC coming into the top bus bar. It is fed to the inverter by the top 60 amp circuit breaker. That next circuit breaker that's ganged to the third circuit breaker, and these, by the way, would be 2-pole breakers for 240 volts with this particular system. But this is a somewhat simplified diagram to make it a little easier to follow it. And what happens is if you need to shut down the inverter, but you don't want to lose your bypass loads or standby loads, you can simply connect a short circuit between the AC in and the AC out bus bars. That's the top red one and the middle red one, by flipping that 60 amp breaker on, and that turns the bottom one off. So it's the only possible way that can be run. Well, sometimes you can run with both of them off. Otherwise, it's top one on, bottom off, or top off, bottom on. And that's the normal operation with the top one is open and the bottom one closed. And in bypass, the top is closed and the bottom is open. Okay. This was a great concern early on because nobody really knew whether the inverters were going to last through a lot of punishment. Folks have found that the inverters don't fail very much these days, and there are systems going in without the bypass switch now. It's still a good idea to do that. You see, we're feeding a 60 amp breaker that connects to the bus bar in the distribution panel, which leaves any leftover electricity available for use by those loads if the standby loads have used what they need. So here's our system schematic based on the design we just did. So quick wrap up, 80 volt on DC side, need an arc fault protection. National Electrical Code requires that. Rooftop junction box, you want a 90-degree terminal strip in there. Otherwise, you have to derate your wire to the ratings of the terminals. Again, I'm clicking through these kind of quickly because I don't want to lose out on time at the end of the program. We've got 25 minutes to go, and we're doing about right. So here's your user variables you can program at the end. You look at your battery requirements, and typically a charge controller is going to have a bulk charge rate at 57.6 volts, a float voltage of 54.4, and that's it for the charge controller. The inverter itself is a little bit fancier as far as charging batteries. You normally want to set the bulk to only 52, and the reason is you don't want the inverter charging your batteries. You want the sun to do that. Okay? But if the sun doesn't get them charged, then you pick up at 52 volts and let the inverter do it. And float 51.6, that simply is like the float voltage gives you what's the equivalent of a trickle charge. The LBCO is a low voltage cutoff voltage. And programmed typically at 44 with lead acid batteries. So that means if your batteries are up to 44 volts, your inverter shuts down. And it does not start up again until the voltage goes up to 50 after the array has had a chance to add it the next morning, or utilities had a chance on it if the utility comes back on. Okay, so these are just some typical programming situations. All right, next example. Another battery backup based on available roof space. I'm going to go through this one kind of quickly because it's basically the same thing, but it's saying, okay, rather than selecting the loads, let's just put as much up on the roof as we can and then see how much it'll run. Okay, do this one in Burlington. Here's the design parameters. We use a 300-watt module, 24 of them up on the roof, assuming that's what will fit, 45 degrees on so far. Excuse me. So we now, first thing we want to do is estimate this 7,200 watt array based on our choice of 24 300-watt modules that just fit just right on the roof. Okay. What do we get to the charge controller based on NREL SAM? Okay, well, here is what NREL SAM says if you run the simulation. All right, it says in January, you're going to get 600 kilowatt hours. February, you're going to get about 690. In March, you're up to 900 and something, okay, and so on. All right, so this is what you can get, and that adds up to a total output from the charge control of 9,191 kilowatt hours. That it would be nice if we could use it all, so let's see what we can do with that 9,191 kilowatt hours. Well, gee, if you had 10% round-trip battery loss, if we're using this as a battery backup system, 6% loss in the inverter, 6% in the wiring, well, gee, then we're only going to get 7,620 kilowatt hours per year that are usable because of all these losses, using it as a battery system. Okay, so 20.9 kilowatt hours a day. Well, okay, well, at least we know that's kind of what we have. That's on average. That's not every day, obviously, based on the graph there. So let's see what we might be able to do with this. Here's some proposed standby loads. Again, you just keep it throwing them in. Line 1, line 2, kilowatt hours per day. See what you come up with. And then we're going to see if that, if this is too many, we take some off. If it's not enough, we can add some on in order to see how we do. Notice the kilowatt hours per day here is 16.2. And what did we have available in that last slide? Let's just quickly back up to the last one viewed, and we had 20.9. Okay, on average. So that means that for a lot of the months here, we can probably meet the needs of these standby loads. All right, so again, same thing. Here we try to balance the loads again. And we got 33.5 amps this time on line 1, 34.2 on line 2. This is about double what we had last time, isn't it? Everything's about double, so we'd expect an inverter would have to be about double the size, and lo and behold, that's what we're going to end up with. Batteries, again, same procedure. We now have 16.2 kilowatt hours now. So delivered to the inverter from the batteries has to be 17.6. Okay, in order to get 16.2 out of the battery, the inverter, sorry. Okay, so 17.6 from the batteries. Doing the math, That means batteries have to have now be rated at 458 amp hours instead of 256, okay, at 48 volts, or 216, I guess it was. If no temperature or charge discharge derating is involved, sometimes if it's cold or whatever, you have to kick a little extra on for the batteries. So we're looking at 458 amp hours at 48 volts. All right, and there's lots of ways to do that. Take a 256 amp hour and do 2 strings of 8, get 512. That's one way to do it. And that gives you a little extra storage. And who's to say whether you want a 1-day storage, 2-day storage, 26.8 hours, but this is kind of a typical design. And or maybe you can derate if the batteries get a little cold in the winter, if they're outside or in the garage, or you can maybe run a higher load. Anyway, but anyway, this is one way to go. It's 512 amp hours. And you can charge them at 115 amps from the charge controller. And that means it takes 4.5 hours to charge, which is close enough to the 5 hours for charge that it's okay, because more than likely you're not going to be charging at that rate all the time anyway. So it should be okay for lead acid, it should be okay for lithium. Okay, and lead acid power watt output should probably be limited to for that 512 amp hours divided by 5 hours times 48 volts, which is around 5 kW. So this is a little more powerful battery pack. And but again, selecting it was pretty straightforward as long as you take into account what the known losses are expected to be. Source circuits, again, here's your formula now. If you want to figure out using -30 and plus degree Fahrenheit and plus 158 degree Fahrenheit as maximum and minimum, or minimum and maximum temperatures, you convert the Fahrenheit to Celsius, and the formula for open circuit maximum voltage is the 40.1, that's the voltage at 25 degrees C, times 1 minus the temperature coefficient times 25 degrees C minus the low temperature, and that gives you 47.25 volts. And for the minimum voltage, you take the maximum power voltage of 31.6 at 25 degrees C and multiply that by 1 minus the temperature coefficient times 25 minus the maximum temperature, and notice this gives you a voltage of less than 31.6 or 25.2. So 3 modules, you're still good, 141.75 volts. And high temperature, you get 75.5 volts out. So if you have 8 source circuits of 3 modules each, you're fine. So you're almost exactly twice the size of the previous design example. All right. Again, we have to select the source circuit combiner box and a charge controller, and guess what? Source circuit combiner boxes are available that will combine 2 groups of 4 circuits. So therefore, one single source circuit combiner box can handle all 8 source circuits. And but you're going to need 2 charge controllers this time. Okay, and they're going to be 80 amp charge controllers rather than 40 amp charge controllers, because this system is a little bit more than twice as big as the last one. All right, so 20 amp DC circuit breakers, you can get that too. And so therefore, charge controller input current is 38.3 amps, output current 80 amps max. How can it have more out than in? It's because the output voltage is a lot less than the input voltage. Remember, the input-output power, again, for AC transformers, you know the output power is about 98%, 99% of the input power. For good DC to DC converters, the same rule holds true. The output power is good enough to just estimate it as being equal to the input power. If you want to throw in a loss, throw in 2%. That's about all you're going to have. Okay? Maximum battery charging current, 115 amps. C4.5, no problem. Inverter, again, this is going to turn out to be the big brother of the first inverter, the 8000 or VA. Here's your wire sizing calculations. Okay. I'm looking at my clock carefully here. It's 3:45. And again, I just want you to have every single step of the way here available for you to be able to look at again if you're really seriously interested in getting involved in this. Because you shouldn't skip any of these steps if you want to get it right. Okay, voltage drop check, same story. Voltage drop formula is there's this standard voltage drop formula that in most of the electrical handbooks. If not, check out the reference book, the Photovoltaic Systems Engineering book. That's got all that stuff in it in chapter 4. Okay, circuit breaker sizing. Same rules, National Electrical Code rules. We got 12 amp in the circuit breaker sizing. That's 125% of source circuit current. So we use a 15 amp circuit breaker in source circuit, 70 on output. Now battery to inverter, we got a 225 amp because that's a whole lot more power that's being delivered to the inverter. We're up somewhere near 8,000 watts. So we're going to be somewhere close to 150 to 175 amps if that thing is cranking out at full blast. Okay. Here's the DC section of schematic. 8 source circuits. Whoops, what have I done? I touched the thing. I didn't mean to do that. Back up. Last viewed. Okay. The 8 source circuits go into that source circuit combiner box. We combine 4 at a time. They go to 2 different charge controllers. You can follow that wiring diagram more closely when you, if you're really fast, you can do it right now. Otherwise, take a look at it when you order up the PDFs. And it goes to the inverter. Okay, just that straightforward. The other thing that's missing here, you got ground fault detection. You may have to have an arc fault circuit interrupter in here as well, but that would be in this component enclosure. Okay, the AC part. You can see we've got a main distribution panel, 225 amp. What we're doing is feeding it at the bottom with a 2-pole 60 amp breaker. Okay, feed it at the bottom because then when the current comes in at the top from the utility, it comes in from the bottom from the PV system, and whatever comes in from the bottom doesn't have to come in from the top because the top can never provide more than 200 amps. And therefore, if you connect to 60 amps at the bottom, and you're allowed 125% or so anyway, so 125% of 200 amps, it goes by the inverter rating, not by the circuit breaker rating. So as long as your inverter output is not more than 25% of the bus bar rating, then you're okay. Again, the inverter bypass switch in that center orange box, and the distribution panel, the standby panel at the bottom. And again, you can trace through these circuits. If you order it, we have to move at this point because I want you to see a few more things. Rapid shutdown, we've mentioned it a few times. I think it was 2014 that first came into the code on PV. Maybe it was, no, I'm quite sure it was 2014. And this time they did the thing right. They said you need to provide rapid shutdown, and this is a function it has to perform. It has to shut down the array at least no more than 10 feet from the array. They've since changed that in 2020 code. Now you have to shut it down at the array, and you kind of need to read the details. It changes every year, or every 3 years. So it's important to read the National Electrical Code and see what the present, and of course not all jurisdictions have adopted the 2020 code yet. Some are still on 2017, some may still be on 2014. So you need to see what the jurisdiction is requiring in terms of the code. And then you need to be able to implement it. So this is one way that it can be implemented with the birdhouse, which is kind of a neat little thing. And it's simply what it needs to do. You need to shut off everything if the fire department says you got to shut down. So that means you need to shut down your array. It means you need a switch close to the array. You need to shut down your batteries. So if you shut off your main disconnect, that should shut off everything else. But if necessary, you can go to that birdhouse and that'll shut off the rest. And so you have to have signs that tell you where to go to look for the shutdown. Okay. The DC coupled system, now some people have simplified it a bit. There's an inverter out there that does this. It's a 5 kVA inverter, 12240. And it'll give you 24 amps continuous AC out. It's got a built-in short circuit combiner with maximum 20 amps. Okay, and to a charge controller built in with 250 to 600 volt maximum power point tracking range. So here we were exceeding that 150 volt range that some of the inverters have. This one is allowing up to, and some charge controllers also allow up to 600 volts, by the way. That's an engineering design choice. This inverter has integrated arc fault circuit interrupter, ground fault detection interruption, so you don't need all these outside boxes. They've crammed it all inside one case. You can charge batteries with free PV or utility. You've got multiple battery options. Program it, decide whether you want to use lithium or lead acid or whatever. Lots of different operating modes, programmable, including grid support, meaning that if you want your batteries to come on in the afternoon when you're starting to pull a lot of current from the grid and provide you with battery power to minimize your drain on the grid, because the utility says we'll pay you 20 cents a kilowatt hour for every kilowatt hour we don't have to sell you during that time or whatever. It's programmable to do that stuff. You can optimize it for time of use. It's in an outdoor enclosure, and they're stackable. So that is a nice little system. So what you've seen for the design examples are history, because that way you see what's in the guts of the system and what goes into creating a system like the one we're looking at. Here's a picture of one. Battery cabinets. These are DC battery cabinets. The inverter takes in DC from, so it's a DC coupled battery backup system. It's standby loads. The inverter's got all that good stuff in it. Standby loads, whatever you want, however you calculate it. The battery systems can be configured for a lot of different kilowatt hours at 46.8 volts. And that is not lead acid battery, that's lithium. 96.5% round trip battery efficiency here. Okay, again, lithium, 90% for lead acid, 96.5 for lithium. Continuous battery power at 17.1 kilowatt hours, you can drain 6.7 kilowatts. Okay, and each cabinet will give you 17.1 kilowatt hours. So you're looking at 13.4 kilowatt hour or kilowatts of power that will run electric heat, 10 kW electric heat, for goodness sake. So here's a DC coupled system, all in one. 8 kW rated for the inverter, so that's all the kWs you can get out of it in the backup mode. The array, you can connect up to 15 kW of array for a single inverter, and these arrays are inverters are stackable. All the function it needs, including remote monitoring and control. Pretty fancy stuff. So I'm sorry I wasted all your time with all that old stuff when all you have to do is this. On the other hand, now you understand where this came from. After struggling through those systems, and there's still nothing wrong with designing a system like that. There are people who still design and install them. On the other hand, people are really picking up on this new stuff. In particular, what people are, Urban Solar, by the way, is a local company that are staying very busy during the pandemic, preparing for the hurricane season with folks who want battery backup. So let's look at an AC coupled battery backup system. Here's a schematic. We got batteries. We got AC array feeding a straight grid connect inverter, as we saw in that second picture at the very beginning. That inverter is connecting into a standby panel, which is connecting to the AC out of a standard battery backup inverter, but this shows all the switching that takes place. The point of utility connection, you see there's a 2-pole switch there. And when utility goes down, that inverter senses that and it opens that switch. And when it does that, it closes the switch to the generator so that the generator, when commanded or controlled, it will turn on. So what's the deal on this kind of a system? Pretty straightforward. You notice that these are straight through connections. There are no losses in that inverter between the point of utility connection and the standby panel, because it's just wires and switches, not diodes and electronic stuff that is going to give you losses. Notice there's no fancy charge controllers. The batteries are charged by the DC coupled battery backup inverter. That's it. That inverter is in charge of taking care of the batteries. So there's 4 different operating modes. One is the grid's up, sun's up. In that case, the grid is fed through the battery backup inverter to synchronize the grid connected inverter, and that makes electricity. The electricity goes to the standby panel. Any leftover goes back to the main distribution panel. Anything left over after that goes back to the utility. If the grid is up and the sun is down, well, then the sun doesn't make any more electricity, so the grid is just fed straight through the grid connected inverter to supply all the loads, including the standby loads, by way of the battery backup inverter. The batteries are not used unless you have a deal with the utility where you specially program the batteries to come on to reduce some of the peak loading. If the grid is down, the sun is up, then the battery backup inverter has to disconnect from the grid. But it does supply grid quality voltage to the standby panel, and the grid connected inverter thinks that battery backup inverter is a grid, so it makes lots of electricity and supplies it to the standby panel and to the battery backup inverter for charging the batteries. And if the grid's down, sun's down, then that's interesting because the batteries have to handle it by way of the battery backup inverter, and we need to make really sure that we don't drain the batteries all the way, because then there's an interesting problem trying to wake up that straight grid connect inverter when the sun rises the next morning. Okay? So there's some limits here and some communication requirements here. One of the limits on the loads is the amount of pass-through capacity of the battery backup inverter, because when the sun is down, the standby loads have to come from battery backup inverter. I'm going to go quickly here because I want to get to the power wall. Again, these are pretty readily readable. Okay. So here's some design rules. Okay. So these might be the standby loads, same ones we had last time. The only difference now is we're listing how many kilowatt hours do they use by day and how many by night. And the reason is because the daytime kilowatt hours I use because they're generated by the straight grid connect inverter with only about 2% losses. So the more we can use during the day and the less we can use at night, the more efficient the system becomes, and the more of those 9,191 kilowatt hours we can actually use. Okay? So we use the 8,000 VA battery backup inverter, size the array. I want to get to the next slide here, though. If we use that 7.2 kW array, we get the That's going to work for 10 months out of the year. These 2 months, November, December, we can't meet all of the load requirements for the standby loads with the 7.2 kW array in November, December, okay? But notice that if this thing operates with the batteries every day and not connected to the grid, we only deliver 6,213 kilowatt hours. But that's not the way it's mostly going to operate. Mostly, it's going to be connected to the grid. And if that's the case, if the grid never goes down, we can make 9,191 kilowatt hours a year. So somewhere between 6213 and 9191 is what we're going to use, and it all depends on how much we use those batteries. If we don't use them, we get 9191. If we use them, we get somewhere between 6213 and 9191. So that's the rest of the story here. And it's a matter of whether we want to do some load shaving, turn on the batteries in the afternoon, to let the utility even turn on our batteries in the afternoon as a load shaving exercise. That would be the equivalent of turning off a swimming pool pump or a water heater, but instead turning on the batteries, okay? Probably use the same battery size because you want to handle all the standby loads that the utility is down. And that means it's by way of the inverter, so it's the same old thing about the losses from that inverter and the battery charging. The array, the grid-connected inverter, can be at 6,000 volt amps instead of the 7,200 because, again, the array is never going to put out the full 7,200 watts. And standby panel, 100 amp panel is going to work just fine. Here's a three-phase system. And again, take a look at it. This is here just to show that, yeah, it's possible. There are inverters that talk to each other and tell each other. One of these will go to the master that says, I'm the zero phase, you got minus 120 and you got minus 240. And they keep maintaining their phase relationship. And that's up to the battery backup inverters to do that. Okay, but there are a number of them out there now that know how to do that. Okay, these systems are scalable. Just read the manufacturer details, the ones we first looked at. You can put 10 of those inverters in parallel in a 120, 240 volt system and get 80,000 watts of available power. You can put nine of them and get 72,000 watts in three phase. Sometimes the batteries, sometimes a group of inverters or certain inverters will need independent battery systems, so you don't necessarily use one battery system to power 10 inverters. You might have to use two different battery systems or even more, okay? So you need to watch out to make sure you don't, by mistake, use only one battery system if you need more than one. Powerwall, wanted to make sure we saw this thing. It's just an AC coupled system. The Powerwall itself has a DC in from PV. Actually, it doesn't. It takes in AC and it gives out AC. And it doesn't have to have a rectifier. It connects directly into a combiner panel. And according to the control in the system, the Powerwall decides whether it wants to take on power to charge its batteries or whether it wants to deliver power to the rest of the system. There's an automatic relay here that is used to disconnect from the utility if the utility goes down. And the uninterruptible loads then are served by the Powerwall. It's fairly straightforward. You have as many AC sources as you want in that combiner panel, provided that they all meet the requirements of UL 1741. Okay? It is possible to design these systems with enough power walls to back up an entire dwelling unit. There's advantages and disadvantages to doing that. The only disadvantage, you use extra power walls, cost you a little extra money, but the advantage is if you want to run that 5-ton air conditioner, you can do it, if you've got enough of a PV array to keep the system charged. So the design exercise goes exactly the same here as it does on that AC connected system in terms of the PV array size. The difference with the power wall is that you don't need a PV array if you just want some backup power for as long as the thing will hold it until the utility comes back on, as long as the utility comes back on within the next day or so. But if you want it to run continuously during a prolonged power outage, connected to the PV array. Okay, so you use straight grid connected inverter PV array into the combiner panel. And you got internal AC to DC control, the rectifier in there. You need that because you got AC in that rectifies it to DC to charge the batteries, that then it comes back out by way of an inverter to power up the loads. So we are about done here, folks. Here's the way it works. This is readable, believe it or not, and you know we're at the 406 mark, so we got to finish up here. Here's what one looks like on the wall. What's next? Who knows? A lot more communications and controls is going to come on, more sophisticated utility bidirectional interaction is going to happen, integration with other sources and systems. It's going to happen, I don't know, moon, sun, planets, stars. In any case, I hope you all be a part of it because it's going to be pretty exciting. I wish I were younger than 76 because I can tell people about it and I want to see as much of this happen as I possibly can. So that's it, folks. Thank you for your patience. Much appreciated. Let's get to, we've got some comments up here. Let's see what we can do. I will stay around. Yeah, the example, that very last one, those things that you notice, it said Tesla on the box. Those were Tesla power walls. They give somewhere in the neighborhood of AC round trip, what is it? 13.5 kilowatt hours or something for each one of those boxes. And you can have 8 or 10 of them in parallel, so you can store a lot of kilowatt hours. Okay, so yes, that was. There's some comments up here on the chat box. Let's see what we got on chat. Okay, pay attention to this chat because the quiz link is on the page of the webinar. Certificate is there. You can have questions and comments and so forth come in. And I'm really happy you were able to join me this afternoon, folks. It would be, it was a lot of fun. I have to admit at this point, this is the very first time this particular presentation has been given. I knew it was going to be long, but I wanted to make sure you had all of the information so that you can go back over it if you're serious about wanting to design these things, because it clearly cost effective for the future. The payback analysis shows that even with the power walls, the systems are paying for themselves in about 8 years and they last for 25. So there's no reason why anybody should not want to have one of these in a new or even retrofitted dwelling at this point. Okay, there's a live answer to that one. Let's see what we got here. Okay, got that. No more Q's and A's. No more. Oh, here's some chat over here. All right. Well, again, thank you all for joining. I'm looking at the count of participants. I'm going to stay here until that count drops to 2, just in case anybody has any additional questions. Payback is with subsidies. Yeah, it's with subsidies. But that's an interesting thing because you see, The battery backup is actually an insurance policy, and it's not even fair to include that as part of the payback analysis, but it is included in the payback analysis, assuming that you're maybe going to take advantage of some time of use pricing and whatever. So yeah, good point, excellent point. 26% subsidies, they're going down. But right now, photovoltaic power is the going price is something less than 6 cents per kilowatt hour. In order to get your money back on the system, that's what you'd have to sell it for. And natural gas is something a bit over 6 cents. So PV and wind are now cheaper than any of the fossil sources. So there's no reason not to install them. They're clean. They're the solution. They're the future. I mean, I'm preaching. I'm sorry, I shouldn't do that. But let's see. Is a basic linear circuit analysis question on how to arrange the batteries. The batteries themselves, they just are paralleled. And if you connect them, they have the connections already made for you to connect them back to back. Or, you know, just like the modules have plus and minus connectors on them. You have to be really, really drunk. You're going to fall off the roof before you get in a bad connect the modules wrong. Same thing, if you're talking about power walls or on batteries, it's a basic linear circuit analysis problem, but if you have more than two parallel or two series strings with lead acid, then it gets to be a little tricky on how to do that, and I refer you to the chapter on battery backup systems in photovoltaic systems engineering. Hopefully it's available from your library. If it's not, put that in your comment and with your email address, and I can send you a battery management. See, lithium, they're all sealed battery management things because they have to charge cell by cell to keep everything absolutely uniform. Lead acid is a little different story, so you want to make sure you're a little bit more careful on how you hook up when you have more than one series string of lead acid batteries. And that's my answer to that one. And let's see, we talked about payback. Done with that. Batteries, yeah. Okay, anything else? Still some participants. Okay. Oh, how do you sign out? Folks, if you want to sign out, up in the top of your screen under More, at the very bottom, you click on More. At the very bottom of that column, it says Leave. And you click on Leave, and then you go to the PDH website and pick up all your goodies. Okay, so find the More if it's at the top of your screen or the bottom. Anyways, under the More icon, hover over that. It gives you options of chat and a bunch of other things at the very bottom. It gives you a chance to leave. What do we have here? Q&A, another one. What do we got? Yeah, I agree. It'd be nice to be 3 hours. And I would appreciate you. Do you think I should take some material out of it? Or let it be as is and depend on people who are seriously interested to order up the PDFs of the slides. It helped me to know that because I wanted to make sure you had everything you needed to know exactly what's involved in the design. And I wanted to give you several different kinds. All right, so like I say, there's a couple participants left, only 2, but if you have any suggestions on how we can improve, we are into quality control to the extent possible. Put them on your comments. So We want to do everything we can to keep everybody as happy as possible. I didn't spend 35 years as a college professor to make people unhappy. All right, well, thanks everybody. I am going to click on my leave button. I think we're done here. And yeah, we're good to go. Okay, here we go. Thank you again. Stay safe. And hope to see you in the next webinar.